Hello friends, welcome to my channel. So today I am going to discuss the construction and working of a homopolar motor. So what is basically a homopolar motor? A homopolar motor is a device that doesn't require a commutator or doesn't require commutation. What is commutation? Commutation is used generally in AC generators and AC motors where the current keeps changing its direction. So a commutator is a device that blocks the change the direction or creates a net effect such that the current doesn't change its direction with respect to the circuit. Okay, so here we'll be discussing the construction and working of the simple homopolar motor. Okay, this wire I have taken it to be of rectangular shape. You can take it of any shape. You can take it to be a cardioid, a heart, or anything else. You can see the demo videos available on YouTube for the construction and the real life experiment that is done for constructing such a device. So here there is a cylindrical magnet attached to the base of the uh, cylindrical cell, and then there is a cell that is required for supplying current to the circuit, and there is a circuit, you can say this circuit is a rectangular loop. Okay, this circuit is a rectangular loop in which the current travels, and we know that since there is a magnet, there is a current carrying wire, that would be some force acting on the loop, and this force would turn the wire, would exert a torque about the z-axis, and would try to rotate the loop with an angular velocity of omega. Okay, so the loop starts rotating and it works as a magnet. Now here a homopolar motor is a direct current electric motor consisting of current carrying circuit in magnetic field. That is a basic construction. Now here the circuit is free to rotate around fixed axis so that the angle between the current and the magnetic field is constant in time in each part of the circuit. Okay, the resulting EMF is continuous and homopolar motor needs no device like a commutator to switch current flow. So we know that it doesn't needs any device to change the direction of the current like a commutator. So what we have to find? We have to find the torque acting on the circuit, and second thing we have to find the omega as a function of time. Here you can see it is the magnet of magnetic moment M, and since the magnet is having a cylindrical symmetry, or the whole system is having a cylindrical symmetry, we can easily say that we'll be using the cylindrical coordinate system for dealing with such a system. Okay, such a circuit. Okay, now come to the next part. So here I just drew the you can say the important part of the circuit, the more important part of the circuit, and I drew only the half part of the circuit. Why I drew the half part? Because the system is having a cylindrical symmetry about the central axis. Once we deal for half, we will be dealing for the full part. Okay, so let us say that the length of the magnet is L. Length of the magnet is L. The value of phi, okay, since we are using the, we'll be observing only half of the circuit because of symmetry in the problem. And the second thing, we'll be seeing the situation in a cylindrical coordinate system. Okay, so basic overview of a cylindrical coordinate system is given here. So what is a cylindrical coordinate system? A cylindrical coordinate system, if a point is to be located in a cylindrical coordinate system, it coordinate is given by, suppose we need to write the coordinate of a point, of this point, let us say this point is P. Okay, now we need to find the coordinate of P. The P could be written as R phi Z, that is the radial component of the point is R, the height of the point is Z, and it is making an azimuthal angle of phi. So here we can say that R cap is pointing in this direction, phi cap is pointing in this direction, and R cross phi cap is pointing in the Z cap direction. This is very important, and I will be using it in the upcoming part. Okay, now here you should remember that where is R cap, where is phi cap, and where is Z cap. Okay, so this was a small review of the cylindrical coordinate system. Now here writing the coordinates of point A in the figure, we can say that the value of z for the r for this point is 0. The value of azimuthal angle, we call it phi. Okay, for any points, let us say E, F, D, C, for all points phi would have the same value. Phi would have the same value. Okay, so here B, now points, the point F, the coordinate of the point F could be written as B phi 0. That is the value of r is B. Here is point F, and the value of phi, that is the azimuthal angle, is phi only. I just told that the value of phi would be same for all, and 0 because that is 0. Now one important thing that we'll be using later, but here we just discuss that what is z equal to 0 plane. The r5 plane is called the z equal to 0 plane. Okay, so where the value of z is equal to 0, that is called the r5 plane. So r5 plane, if you see the diagram, you can say that in the r5 plane, very near to the r5 plane and very near to the z-axis, the field lines are pointing upwards, straight upwards. Here in this figure you can see this part of the figure, they are pointing straight upwards, and in the outer region they are pointing straight downwards. So here we can say that they are pointing straight upwards, and here they are pointing straight downwards. So phi component of the field is 0. Okay, now B R phi comma 0, that is z equal to 0 plane B naught z cap for r less than B, and for r greater than B we don't need to talk about that at this point. Okay, so this is some approximation, these are the some approximation that you need to take while solving the problem. Now second thing is, if the current, if the wire is carrying current I, the dl vector, we know that the dl vector and the current in the parallel direction are in the parallel direction, so dl will be pointing in the direction of the current. Now we know from the Lorentz force that B cross dl I dl cross B would give us the direction of the Lorentz force. Here you find dl cross B, and it would be pointing out of the plane. The df vector would be pointing out of the plane. Okay, that is in the minus phi cap direction, minus phi cap direction. Okay, I already discussed that where is phi cap. Phi cap was in this direction, so minus phi cap would be in this direction. Okay, so one important thing, that r cross phi is z, r cap cross phi cap is z, that is also very important thing. So here to find the direction of the torque, we do r cross df, and r cross df, you once do that, here r cross df would give you the value of torque that would be pointing in the minus z cap or z cap direction. So dl cross b is minus phi. Here see this figure and answer the following. So b dl sin theta would be the value of dl cross b. Now here minus phi cap b dl cos psi. How it came to be cos psi? Because theta is equal to psi plus pi by 2. Now sin psi plus pi by 2 would be equal to cos psi. Now b dl cos psi, now we assume one vector which is perpendicular to dl always, and let us say that this is n cap. So what is n cap? N cap is a unit vector which is always perpendicular to dl. Okay, now here we have to understand that if dl is taken like that, n cap is taken like this, that is that means that we have to take the angle like this. Okay, you have to understand the sense of angle also, because it is also very important aspect in taking n cap at different places. Okay, at different parts of the loop, suppose OC and then CD, then DE, then EF. Okay, at different parts of the loop, n cap and dl would have some different directions. Okay, now here we write the torque is bmi a to f. Now what is a to f? Here you can say that a to f, we completely traverse the circuit from a to f. If we go from a to f, we completely traverse the circuit, then f to o, then o to a, we will be forming a complete closed loop. We will be forming a complete closed loop if we travel from a to f and then f to o. Okay, so we'll be writing the torque on the whole circuit if we just do the integration upon a to f then f to o. Okay, so this would give us the torque, and let us talk about the next thing. Okay, so here we will say that bm is a constant. Bm is a type of constant. Okay, bm is a type of constant, and BMI R cross DL cross B, and we know that it's pointing in the minus z cap direction, so minus z cap BMI A to F B dot n cap RDL. Now here we can say that for the closed path AFO, for the closed path AFO, the value of the closed integral B dot n cap RDL is 0. For the value of the closed integral b dot n cap rdl is 0. Now how I came to this conclusion that the value of the closed integral would be 0? Let us discuss this idea. So first I break the closed path integral into the path components, that is from a to f b dot n rdl, then f to o b dot n rdl, and o to a b dot n rdl. Okay, now we just broke it into components from a to f, f to o, and o to a. Okay, now here what we do, we need to find the value of the integral from a to f. Okay, for finding the value of integral from a to f, we need something important. Okay, so from a to f or o to f, suppose we go from o to f. Okay, so from where to where we are going? We are going from O to F. Now seeing this figure, we can say that we generate a cylinder. We need a okay. How will be proving that the closed integral would be 0? That would be discussed here. Okay, here I will be discussing that why the closed integral came 0. First for all, let's go from O to F. So along OC, we can say that DL vector is pointing upwards, n cap would be perpendicular, and B is also upwards. So B dot n cap RDL, B and RDL would be 0. Okay, R would also be 0. So along OC it would be 0. So along CD, now along CD we can say that DL is equal to DR, DL is equal to plus DR. Here you can see DL is equal to plus DR, and n cap vector would be pointing in this direction. B dot n cap would be 0. Okay, B n cap RDL, B dot n cap RDL. But since the magnetic field is parallel only very near to z axis, very near to z axis it is parallel, otherwise it is changing direction everywhere. Here it would be somewhat like this. Okay, so we will be using B dot n cap, not the value of angle. We will not take the value of angle to be 0. So along DE, now let us talk for DE. Along DE, we can say that we are traversing in the minus DZ direction. So minus DZ direction, we just do that along DE. P dot n cap Z dz from D to E, and minus came outside. Okay, Z dz minus n cap. Okay, BNRDL, that is what we are finding, BNRDL. Okay, so B N Z dz. Okay, I hope you understood what I wanted to tell. Now let's come to the next part. 1 minute, I think there is some mistake. There would be not Z dz, it would be R dz. Okay, it would be R dz. Okay, you just correct that, it would be R dz, and here R dr is correct. Okay, so from E to O, it would pointing in the minus dr direction. So BNR dr from E to O. Okay, now reversing, you know, the from definite integration, the rule that if minus is outside, we can interconvert the uh, limits of the integral. We can say it is from O to E, and we can say it is from D to E. Now close integral B dot n cap RDL, B dot n cap RDL from O to C, C to D, and D to E. How it came D to E? We just reverse the sign of the integral. Here it would be E to D. Okay, E to D. Okay, now here this is the value of the what, our integral. Okay, now this is 0, this is 0, so only these three integrals are left out. Okay, so we need a cylinder. Okay, what we do, we just rotate the loop around the z axis, the loop OCDO, the loop OCDO is rotated along the z axis to generate a cylinder. Now we need to write the flux through the cylinder. The flux through the cylinder would be written as B dot n cap ds upper surface, lateral surface and lower surface, and this would be 0 because the value of divergence of magnetic field is 0. So the net enclosed flux through a closed surface must be 0. Here we have assumed that the radius of the cylinder is a. Okay, so the value of the radius of the cylinder is a. Now through upper surface we can write at this point, at any point on the upper surface, the value of r would be r, phi would be phi, and z would be h. Okay, now here we wrote the magnetic field and r dr because the surface integral would be the ds vector can be written as 2 pi r dr. Okay, now here for the lateral surface we can write 2 pi r dz. The lateral surface would be like this, a ring would be there, ring surface. So expanding this, opening this ring about any point, we will get a rectangular strip of area 2 pi r dz. So here we write the flux from 0 to h, 2 pi r dz, and then we write the flux for the lower base, that is b r phi 2 pi r dr. Okay, now for the lower base it is again a cylindrical, a circular ring. Okay, now we take 2 pi as common, and the remaining thing inside the integral 0 to h and all other things would give us this integral. Okay, this part of the integral would give us this part of the integral, and this part of the integral, okay, this part of the integral is the value of closed integral b n r dl. Since it is 0, it is 0, this value is 0, the remaining, that is c to d, e to d, e to d, and o to e, b and r dr would give us the closed integral b n r dl. That means closed integral b n r dl would come here, 2 pi would go here and make a 0, so b n r dl is 0. That's why we have used the fact here that the value of these integrals, the sum of these integrals would be 0. Now the main equation is this equation, equation number a is the main equation. We'll be using this equation. Okay, now here from equation number a we can say that the closed integral would be 0, a to f b n r dl, o to f b n r dl, and o to a b n r dl. Now o to n we can say that line integrals on the z axis are 0 because b and n cap would be normal to each other. Okay, now here we can say that, okay, from a to f the value of b n r dl would be the value of minus f to o b n r dl. Now fo, on fo we can say the value of dl is minus dr, so fo is somewhere here. Okay, fo is like this in the cylindrical region, the magnet fo, in the cylindrical region of the magnet fo is somewhat like this. So in this direction it's the minus dr direction, so dl would be equal to minus dr, and b dot n cap is minus b naught, minus b naught. Okay, why this? Because b is pointing in this direction, b naught is pointing in this direction, current is going in this direction, dl is pointing in this direction, therefore n cap would be pointing in this direction. Now b naught dot n cap, b naught dot n cap would give us minus b naught because angle is pi, so cos pi is minus 1, that's why we're getting minus b naught. So here we just integrate it from 0 to b, b naught r dr, and it's minus b naught b square by 2. Now this is the value of integral a to f b dot n cap r dl. Now we put the value of this integral in the torque equation. Okay, now we put the value of this integral in the torque equation. So putting the value in the torque equation, here we'll just get minus z cap bmi b naught b square by 2. Okay, now we will be putting it, but not right now. At this point of time I am not going to put it here, but we will be putting the same value of integral here. First we need to find the emf due to rotation. What is the emf generated due to rotation of the loop along a fixed axis? The emf generated because of the loop, here we will again take the constant bm. Now here c to f, c to f, where was point c? Point c was on the up upper part of the cylinder here from C to F. From here to here we'll go and find the value of the EMF induced, because along the z-axis line integrals are 0, along the z-axis line integrals are 0, so therefore we are not considering A to C. Okay, from C to F we'll just find the value of omega cross R cross B dot dl, because the value of EMF we already know from the basic formulas of JEE, regular JEE syllabus. So here we can say that it would be omega R, omega cross R. So omega is like this, omega is like this, so it is pointing in the upward direction. Okay, let me find the direction of omega. It is pointing in the downward direction. Okay, omega will be pointing in the downward direction, because omega is an axial vector. Okay, omega is pointing in this direction, r cap is pointing in this direction, so r cross omega would be in the positive phi cap direction. Yes, it is correct. R cross omega would be in the positive phi cap direction. R cross omega would be in the positive phi cap direction. Yes, it is correct. So here we will get what, C to F Bm, my since it is B dot dl, will dot dl dot B or dl cross B phi cap dot B cross dl. Okay, here is some problem. Phi cap dot B cross dl, so it is phi cap dot dl cross B, and a minus sign would come because of reverting the cross product. Cross product not revert so easily. So here we will get final as the value of phi cap dot dl cross B, we already found out it to be n cap. Okay, phi cap cross dl cross B was already n cap. So here again the same thing, we'll be doing it, and we'll get the value of induced EMF as Bm omega B naught B square by 2. From C to F we know the value of B dot NRDL is B naught B square by 2. Okay, because from A to F, A to C would be 0. So how I got that, here the value of A to F, BNRDL is given. So we can just break it into A to C plus C to F components. C to F components. So A to C it would be 0, and C to F would be the value of B naught B square by 2. Okay, A to C, why it would be 0? Because it is lying on the Z axis, so the value of integral would be 0. Okay, so here is the value of induced EMF. So here we can find the value of current. Current would be the total EMF divided by the resistance, that is V plus Bm omega B naught B square by 2 plus R. Now the total torque that is acting, first we have taken a torque which is proportional to omega, so we'll write friction torque due to friction as minus eta omega. It is proportional to the friction and it is opposite in nature. So here we'll write total torque I d omega by dt as Bmi B naught B square by 2. How we'll write this equation? We already derived it upwards. You can check, and minus eta omega. Now putting the value of I and other terms, we'll get the final equation of omega as this. Now solving this differential equation, we'll get the solution of the above equation as this, which is omega as a function of time is minus 2 bm vb naught b square by bm square b naught square b to the power 4 plus 4 r eta, and 1 minus e to the power minus t by 4 ri, where I is the moment of inertia of the complete loop or the half loop. Okay, now here it is a type of omega t is equal to minus omega max. So here if we don't consider the minus, it is an exponential rise, and when we multiply any graph by minus sign, it reverts its sign, that is mean it is decomposing. Okay, it is a decreasing omega is decreasing. So minus of exponential rise is exponential decay. So the omega would decrease with time exponentially, minus omega t by this. And if I consider the frictional torque to be negligible, that is eta is very less than here from this term, eta is very less than bm square b naught square b to the power 4 by 4r. Here the modified form of the solution takes place as omega as a function of time. You have to take the approximation, sum of approximation, 2b by bm uh, square b naught square b to the power 4, and above terms they all cancel each other, and finally you are left with the following value of omega if the friction force is negligible, and then you get this. So in the absence of friction, we can say that the steady state, in a steady state there would be no current, that is the value of V and E would be equal. This is the condition for steady state. So as t tends to infinity, omega tends to minus omega naught. So the kinetic energy in the steady state would be half I into omega naught square. So here we will find the value of omega naught square, and kinetic energy in steady states come to be 2v square I by bm square b naught square b to the power 4. Now the value of current could be written as I by r v plus bm omega b naught b square by 2. Now here omega is present, it is a function of time. We put omega as a function of time and we get current as a function of time, and it is a decaying current. So current is also decaying and the velocity is also decaying. Angular velocity is also decaying, current is also decaying. Okay, now the total energy of the circuit contains as the power generated du by dt is equal to IV. So du is equal to IV dt, and from 0 to infinity we integrate that and we get the final solution to the answer, that is V square by R, and integrating this will get T. So putting the value of T will get the final answer. The heat generated is 2 times the kinetic energy. Okay, the total energy of the system is 2 times the kinetic energy. That means that that would be generated, okay, the heat or any other thing that would be generated would be the one kinetic energy, that is k plus k is equal to 2k. So other form of energy is 1k. Okay, now we power dissipated by the friction can be written as torque of friction into omega friction, and this is the work done. This is also same as the work done. Tau d theta by dt is the power generated by the friction is tau omega. Now n omega f square, the final value of omega, we put the maximum value of omega with friction, we get the power dissipated by the circuit. Then we get the value of voltage driven current. The voltage driven current is this, and we get the value of the voltage driven current, and the final value, that is the maximum value of the voltage driven current, uh, from the function. We got the value. Now the power by the source is VIF. This is the value of the power delivered by the source, and power in the form of heat is RIF squared. R is the resistance, and we just do, you can just sum the value of P heat plus P friction, which is this P heat plus P friction, and then you get the value of, once you sum it up, you check it, and it would come nearly to be P source. Okay, I hope you like this solution, and this is the second longest video on my channel, and this question is way harder to think. Okay, but easy, but slightly on the easier side, slightly. Okay, so thanks.